Okay, welcome everybody to our distinguished speaker session as part of our Engineering Week 2021. As you may know that every year we observe the Engineering Week, the last week of the February. So the nationally, and that's how we're doing it. And this week we are doing it different days. We are offering different activities. Today is the Career Day. And welcome to those people who are watching through our live college YouTube channel today for this Career Development Day. And we're lucky to have here one of our alumni, Dr. Mauricio Salinas from the Raytheon, as our distinguished speaker. No? So let me first briefly tell about Dr. Salinas. As you know, we are always proud of our students. No? And as I mentioned, Dr. Salinas is our alumni, and we are really proud of him. He did, when he was here working in the mechanical engineering department, he did the 5 internship with the NASA Glenn Research Center. And after that, he moved to Stanford University for doing his master's in mechanical engineering. And then he started working in the Texas Instrument. And after that, he was also was a designated Raytheon scholar and attended the UT Arlington for his PhD program. So we're going to learn more about him because he's our Valley students, and most of our students, we know that we are proud of you, and we are really proud of our alumni, Dr. Salinas. So I'm going to give him the floor and to talk about and show his presentation about the Raytheon and his work on this area. Thank you, everybody. Dr. Salinas, yes.
Thank you very much. It's so happy to be here. So glad you invited me for this. I really wish this could be in person. This would have been a very good opportunity for me to take a trip to the Valley. I moved away from the Valley over 20 years ago, so any chance I get to go back, I try to jump on it. So maybe I can come visit next year. I'd like to start off by telling everybody a little bit about myself personally before I get too deep into any of the technical stuff. Let me see if I can share my screen here. Everybody see my screen okay?
Yes.
Okay. So my family and I are originally from Durango, Mexico. The picture you see there on the left is me on my 3rd birthday in our home in Vicente Guerrero, Mexico. And shortly after that picture was taken, we moved to the Valley. And actually we moved to Edinburgh, Texas, really close to the UT RGV campus. You see there on the map on the right, you can see the campus, and a few blocks to the east was my childhood home where I grew up. And I actually lived there until I graduated from UT RGV. My family built an A-frame home in that corner of 10th and Lovett, and that home is still there. We sold it many years ago, but that home is still there. So really, I grew up in the Valley, so I'm really a native Valleyite, I guess you could say. So like I said, we moved to Edinburgh, and so I graduated from Edinburgh High School. And actually in 1990, the year before I graduated, was the very first year that UT RGV had an engineering program. So I from when it started. Ended up as an intern at NASA for 5 summers while I was at UT RGV and during my master's degree. So I was able to, each summer I was able to go up to the Glenn Research Center things I would encourage the students listening today is, if you haven't got an internship yet during your undergraduate degree, I would highly encourage you to do so. There's many things that you'll learn during an internship that you can't learn in the classroom. So if you haven't done one yet, I would make it a priority to do so. So while I was at NASA, one of the things I focused on was doing microgravity combustion experiments. At the time, NASA was designing and building the International Space Station. So one of the things they were worried about was fireways to minimize the propagators. So in order to do that, what you have to do is to study how things burned in space or in a low gravity environment. And by the way, why do I say microgravity? Some people will say that there is, zero gravity or no gravity in space, and that's really not true. There's no, as far as we know, there's no place in the universe that has zero gravity. You know, it doesn't matter where you are, you're going to feel the attraction of some body. So we would call it microgravity. Can you all still hear me?
Yes.
Okay. So if you see the picture there, the candle burning on the left is how a candle would burn on Earth. And basically you have this elongated flame because of buoyancy forces acting on the flame. You have natural convection developing around the flame. And so you actually get a pretty large temperature gradient along the flame. The same candle burning in space or in a microgravity environment would burn a lot more in a spherical shape because you don't have the buoyancy forces acting upon it. And the temperature is much more temperature uniformity. And so these are the type of experiments that I was lucky enough to work on while at NASA. And so you ask, well, does that mean that you went to space? And the answer is no. We actually did these experiments on Earth using flying in a parabolic path, which you could see in the lower right-hand graph there. The aircraft basically takes off and does this parabolic shape. And at the top of the shape, and while it's falling, you don't feel the effects of gravity.
I think we might be having some audio difficulties. Mr. Salinas, can you hear us?
I'm sorry?
I think the audio might be lagging a bit. Apologies for that.
Oh, I'm sorry. Yeah, so when you do these experiments on these aircraft, you get about between 22 and 25 seconds of microgravity time. And so you have a very
Apologies, everyone. I think we might have lost Mr. Salinas for one moment. There might be internet issues. Are you there?
Yes. You are muted, Dr. Salinas. Yes.
Oh, how did that happen?
Yeah.
Okay, can you still see my screen?
Yes. Can you close down some of your windows, maybe which you are not using? Maybe sometimes it cuts your.
Okay. Yep.
Okay. Good.
Okay. Okay. And actually, for my senior design project, when I was at UTRGV, I was tasked with designing the wind tunnel that is currently being used in the mechanical engineering department and is found in the high bay area. That picture there to the left is the actual wind tunnel. That's a fairly modern picture that I pulled from the website. And it all started with the pictures on the right. So I used the NASA code to actually design the nozzle and the diffuser, and then actually went and had it manufactured. So you can see those pictures to the right.
Yeah, sorry to interrupt. Like, can you please share your screen so that you can see those slides, please?
Oh,
okay. Looks good. Yes, great. Thank you.
yeah. So you see the nozzle and the diffusers on the right. Those were when I actually had them built initially. So that was my senior design project at UTRGV. Then I graduated from there, and then decided to go to grad school right afterwards. And I ended up going to Stanford. And there's a kind of funny story about how I got admitted to Stanford. While I was at NASA, I got to, NASA does a lot of research, and they invite a lot of professors from a lot of different schools. And so I got to work with a professor out of UC Berkeley. And I actually worked for him for one summer. And after the summer, he invited me to go to UC Berkeley to get a PhD under him. Well, at the time, I didn't want to get a PhD. I only wanted to get a master's because I was a little bit tired. I did 5 years of undergrad school. And I didn't really want to commit to another 5 years of school, or, at a minimum, to get a PhD. And he said, no, I don't take master's students. I only take PhD students. He said, you can go work for my friend at Stanford. So that's how I got into Stanford. So when I went to Stanford, I went with the idea of studying combustion because that's what I had done at NASA. But when I got to Stanford, Stanford is in the middle of Silicon Valley. And at the time there was, the whole internet and electronics boom going on. So a big topic of the day at the time was electronics and electronics cooling. And so I kind of changed my focus to heat transfer and, really concentrated on microscale heat transfer because that was what was needed to come up with cooling solutions for, processors and chips and things like that. So once I graduated from Stanford, I was really lucky and got a job as a thermal analyst at Raytheon TI Systems. TI being Texas Instruments at the time. They sold their defense section to Raytheon. And so I got a job as a thermal analyst, really doing exactly what I had studied in grad school. So I studied electronics cooling in grad school, and that's exactly what I was doing. I was looking at circuit cards, components, high-powered electronics that were going into military systems. You guys still hear me okay?
Yes.
Any questions so far?
No.
No questions. Okay. So at Raytheon, in McKinney, Texas, specifically where I work, one of the things that we focus on are these turrets that you see here. A turret is basically a sphere, basically jam-packed with optics and electronics. And we place these on mostly UAVs, unmanned air vehicles. And so this is really the tool that the pilots use to fly these aircraft. And so, the pilot can be, somewhere in the United States, and these aircraft can fly anywhere in the world. And so there's a lot of engineering that goes into these things. I'm basically going to touch on the mechanical side of it, but there is, electrical, obviously, software controls, and so forth. I'll be touching on the heat transfer and aerodynamics and a little bit of optics on these things. We'll skip that video. So here is one of the turrets mounted onto, I believe this is a Predator UAV. And so the three topics I'm going to kind of mention is thermal management, aerodynamic design, and optical design. Those are the three that I'm most familiar with. So the thermal management portion is, you have this sphere basically jam-packed with high-powered electronics, optics, and lasers and things like that. All of these things generate heat. And so it's, you're fine when you're flying and the atmosphere is nice and cold. But when you're sitting on the runway, say in Saudi Arabia, and it's 140 degrees outside, and you're generating, hundreds of watts of power yourself, how do you cool these things? And, not only how do you cool them so that they don't fail, how do you cool them so that their performance is not degraded? And so that's really the job of a thermal analyst to do that. And I guess when I first started, we were able to, basically use air cooling, use fans and things like that to stir air inside the ball, and we could get away with that. But now, the electronics are getting so powerful that now we have to go to like a liquid cooling system. So that's the type of work that I do at Raytheon. The other aspect is the aerodynamic design. We're sticking this pretty big ball, kind of in front of this UAV. The first question the UAV manufacturer asks is, what's gonna happen to the aerodynamics of my aircraft when you stick this, protruding turret on the front of my aircraft? And so you have to calculate the drag, the lift, and the moment. The moment gives you the torque. If you have enough aerodynamic torque acting on your turret, you could actually, if it's not strong enough, it could actually shear off and fall off the aircraft, which would be a terrible thing to happen. So these are all the things that you have to be able to estimate before you actually build and assemble one of these things and go out and fly it. The last thing is optical design. The optics inside these things, these things are used for surveillance, which is really a fancy word for spying. And you want to see really, really far away. You want to be able to fly really high and see really far and see really clearly. And these optics are getting so sophisticated and so sensitive that, there's a lot of things that we used to not have to worry about that we now have to worry about. And one of those things is the aerodynamics around the window, the front window of the turret. If you have turbulence there, it actually degrades the optical performance. So we have to come up with a design that minimizes the turbulence in front of the window in order to maximize the optical performance. So just really quickly, if you have aerodynamic turbulence, the problem is that the density of the air varies quite a bit. So for example, if you have a glass of water and you stick a pencil in the glass of water, the pencil itself is going to look crooked. Your eyeball is an optical sensor, right? And the density between the air and the water is very large. And so what you get is, optical error, basically. The pencil looks crooked, but it really isn't. And so that's the same concept. And that concept is called near field wavefront error. And that's something we have to deal with in these optical systems. And it's a pretty complicated problem. But we, those are the kind of problems that we have to deal with. A couple of colleagues and I actually were issued a patent on an airfoil that we placed around the front window of these turrets. And this greatly reduced the turbulence at the window. It allowed the air to stay attached to the window and to be laminar. And it greatly improved optical performance. And we were issued a patent for that, which I thought was really cool. Okay, so now we're making the problem much, much harder because we're adding high energy lasers to these turrets. So, they were high powered before, and now we're just adding, orders of magnitude of dissipated heat by adding these lasers. And the reason is because lasers, well, first of all, if you're going to use a laser to shoot something down, you need it to be high powered. And secondly, a laser is very inefficient. And so for every watt of power that you're lasing, you're generating, 2 or 3 times that amount in waste heat. And so you have to figure out what to do with that waste heat. I'd like to show a video of some of the things we're actually working on. Let's see. So, there we go. Can you all see the video and hear it?
We can see it, but there's no audio.
No audio.
Let me stop sharing and see if I can get that to work.
Yes.
Now?
Yes.
So if you watch Star Wars movies and you see, basically shooting things down with lasers, it's no longer science fiction. We're actually doing it.
So I believe these are very high-powered laser, like how much power they have to have the laser to work?
Well, those numbers are classified, but it's high powered.
Like high power means how much? Is this 1,000 watt or more than 100 watt?
Yes, several kilowatts.
Several kilowatts. Okay.
So this isn't, I mean, scientific, this is not fiction. We're actually designing, building, and deploying these laser systems. And so for a thermal guy like me, it's really awesome because, you know, it's very high powered. You have to do something with all that waste heat. And so you have to figure out, you know, come up with unique solutions to do that. And so it's basically job security for the rest of my career. And for those of you interested in heat transfer, it's job security for the rest of your career too. So it's a very fun and challenging problem, which we're dealing with currently. Okay, can you all still see on my screen?
Yes.
Okay, any questions before I move on? Okay. So
I think Mario, do you have a question? I think you are muted. Can you unmute yourself, please?
Can you hear me now?
Yes.
yes.
Okay. I noticed that that weapon is so very fast in aiming. Like, you know, it would pick an airplane and it would instantly fire. Like, is the aim part already developed accurately, like the way it shows it on the video already?
Yeah, we actually have that technology from previous systems. We have a missile system that can detect a threat, fire the missile, and have the missile hit it all within about 0.2 seconds.
Nice.
So
nice.
the targeting system was already in place before we implemented the laser part of it. So that's probably 10 to 15-year-old technology. The identifying a threat, targeting it, and shooting at it, we can do in about 0.2 seconds.
Very nice.
So what I like to do is kind of give you an idea, go over my career path. This kind of gives you one example of one engineer's path. I started at Raytheon as a thermal analyst in 1998, and I started working on the design, thermal design of circuit cards, and then from there I moved up to looking at system level things, like electronics boxes with many cards in it. From there, I started doing the thermal and aero design of turrets, radar systems, larger systems, ground-based radar, up to 10, 20 kilowatts of power. So I kind of moved up the ranks fairly quickly. Took me, 8 years to move up to principal engineer, which is an E5 level. And that's the level where most engineers at Raytheon actually retire. So most engineers will work their entire career and then retire as an E5. At that point, actually, at 2006 is when I started, when I went back to school, and I started working on my doctoral degree. And that took me about 5 years. I was lucky enough to be a Raytheon scholar, so I got, Raytheon paid for it. And I actually got to, for 2 years, I got to go to school full time without any work. And I still got paid about half salary, I believe. And then from there, I came back to work, finished my doctoral degree and came back to work. I quickly after that got promoted to senior principal engineer, which is an E6. And then I was named the section manager of my group. So I manage a group of about 15 analysts that do thermal analysis, structural analysis, and controls. And about the middle of last year, I was promoted to engineering fellow, which is an E44 designation. And that's one of the highest levels you can reach as an engineer at Raytheon. Less than 0.5% of all engineers at Raytheon make it to engineering fellow. So I was pretty lucky in that I got a job that fit exactly with what I was studying in grad school. And so I really enjoyed that topic. And so I think if you do something that you enjoy, you're going to do well at it, and you will move up quickly. By the way, my wife, Mauricio Salinas, she has been at Raytheon for 6 years less than I have. She's younger than I am, and she's already a E6. So she's doing really well too. I've seen lots of engineers being hired from UTRGV, and I've actually hired many engineers myself into my department and into my group, my specific mechanical analysis group. And I can tell you that, the performance of UTRGV engineers is really, really high. I see a lot of them get promoted quickly. I see a lot of chief engineers, a lot of program managers, a lot of lead mechanical engineers. So, really the quality coming out of UTRGV engineering is really high, and we do well in industry. So, if you get a degree from UTRGV in engineering, you're going to do very well. Okay.
I had 2 questions in the chat, if you don't mind.
Yeah, go ahead.
Yeah, so the first question is, you mentioned that it's energy waste. Does that mean that it's just using excess energy accumulated by heat?
I'm sorry, repeat that.
That they're asking, does that mean that the energy waste is just using excess energy accumulated by the heat? And then they were also curious about if that heat is captured or if it's recycled.
Okay, so the energy is generated by either the vehicle or it's generated by a bank of batteries. So we generate the energy on board, and the waste heat is discarded. We haven't, this is very early on in the development of this. We haven't figured out a way to reuse it. But that's a good idea. We should reuse it, and but we have to figure out a light weight of converting it back to electrical energy. Which, because a lot of these things are airborne, right? You're flying around in these small UAVs that can't carry a huge load. So you have to anything you do has to be very light. But yeah, that's probably a problem we'll be solving next. That's a good question. Any more questions? Did I answer them?
I believe so. Thank you so much.
Okay. So the next thing I wanted to do was talk about another project I worked on while at Raytheon. This is on the radar side. So this is a radar on a V22 aircraft. A V22 aircraft is an aircraft that has its rotors can rotate 90 degrees. So it can fly like a helicopter, and it could also fly like a regular airplane. And so they use this aircraft to deploy special operations troops, which is your Green Berets, your Navy SEALs. These are highly specialized troops that go into enemy lines. And so what you do is you fly, you usually do this at night. And so to keep from being detected by the enemy, you fly really fast and really low. And when you get to the spot that you're going to drop them off, you basically, you rotate the rotors, and then you drop down like a helicopter, land, let them all jump off, and then you fly up like a helicopter. And once you're at a safe distance, you rotate the rotors again, and then you fly away like a regular airplane. So this radar that you see on the nose of the V22, it is used to fly the aircraft at night. It's used to track the terrain, because the pilot can't see anything. If it's at night, you really can't see. Sorry, is there a question?
I think not. Can you guys please unmute when you're not talking? Thank you. Yes, go ahead, please.
Okay, so this radar basically flies the aircraft and it hugs the terrain. So if you see this picture on the lower right, you know, if you're coming up on a mountain or something like that, you rely on the radar to fly the airplane, you know, to pull up, to not crash into the mountain. And so, you know, it works perfectly fine unless there's ice. So if you get ice accumulated on this radar, you're basically blinding the radar and you can no longer complete this type of mission. And so generals don't like to be told that they can't do a mission because of bad weather. So they commissioned us to come up with an anti-ice system to always keep ice off of this radar. So this dome that you see in front of the radar is called the radome. So it's basically a dome that's protecting the radar. So this is the opposite problem. Instead of cooling things, we need to heat up the radome in order to keep ice off of it.
We have another question in the chat.
Yep.
They're asking, would it be possible to turn the waste heat into energy using a thermoelectric generator to power surrounding systems?
Yeah, well, basically a TEC, thermoelectric cooler, can convert, you either have a temperature delta, it turns into electrical current, or you can do the opposite. You could have electrical current and convert that into a temperature delta. You can, but that is a TEC cooler or a TEC generator are very inefficient. So you would need lots of them. It would take up a lot of volume and a lot of weight. I mean, if you had, you know, if you're putting this on a Jeep or something, that you could pull a trailer behind you, where you could have some of that equipment, it might be possible. But in an airborne system, it'd be pretty difficult because of the volume and the weight. But that's definitely a good idea. If you could make those more efficient and lighter, maybe you could apply it. Good question. So when we're looking at this problem, when we're commissioned to keep ice off of the radome, we looked at a lot of different things. You know, can we make the radome a certain shape that would keep ice off of it just by the shape alone? Can we spray it with a hydrophobic coating? You know, we looked at a lot of different things and did a lot of research, and basically decided that the best solution at the time would be to simply heat it up so that ice would not accumulate on it. So we actually came up with two different methods. One was a heated air method, where you had a dome inside a dome. And so we'd flow hot air in between the two domes just to heat up the outer dome. And the other method was basically to embed a wire into the radome and heat it up that way. Now, nobody wanted to do the heated wire solution because if you stick a wire in front of antenna, that's the worst thing you could do to an antenna, right? You're gonna dramatically degrade the signal integrity of the antenna by sticking something metallic in front of it. So everybody was rooting against that solution. But we actually overcame it and it worked, so, which I'll talk about. So this was our dome-on-dome solution where you had an inlet manifold and an outlet manifold where you basically flooded it with hot air. And this was a pretty good solution, but the problem with it was that it was very hard to get uniform temperature on the entire dome. And so in order to get a minimum temperature of like, say, 5 degrees C on the surface, you really had to pump a lot of airflow through it at a pretty high temperature to get, you know, a minimum surface temperature of around 5 degrees C. And it turns out that you actually need, you know, a pretty high initial temperature in order to keep ice off of it, because you have what's called supercooled water particles floating in the atmosphere. So these are water particles that are floating around that are at -10, -15 degrees C. And it's a pretty unique phenomenon. How can you have water in liquid state at -10, -15 degrees C? It actually happens naturally in the atmosphere. It's called a supercooled water particle. So anytime that water particle comes into contact with anything, it's going to nucleate and freeze instantly. So if you're flying and you happen to fly into a cloud of these supercooled water particles, you're pretty much going to ice over almost instantly. And so you have to have the minimum surface temperature of your radome be pretty warm, hotter than 5C, in order to ensure that ice will stay off of it. And so this solution was discarded just because it was so difficult to maintain that minimum surface temperature because of the non-uniformity. So we were kind of forced to go with the, oh, am I missing? Where is the heated? Okay. Well, so what we ended up doing was going with the heated wire solution. And so what we had, you know, we could supply enough heat and, you know, it was much more uniform temperature. But the biggest problem was, you know, how do you deal with the signal degradation of the radar itself? And so if you look at that pattern, the wire pattern and the spacing, you know, it took us about a year of analysis to come up with a pattern and spacing that would minimize the degradation of the radar signal. And so, you know, it was pretty sophisticated shape and spacing and so forth in order to not mess up the radar signal itself. So that was another interesting project I worked on. And we actually flew it in icing wind tunnels in Ohio and from Boeing in Seattle to test it out. And it actually worked really well. And then we implemented it on an aircraft and flew it in Nova Scotia in Canada during the winter season. And it worked really well there as well. And this is a picture of me in Ohio. We were doing some of the testing in January. And so I said, you know, every time I went to my car, I had to do de-icing the old-fashioned way by scraping it off. Anyway, I think that's all I had. These are pictures of my kids. questions?
Yes, we have a question from one of the viewers on YouTube. They are asking, how much signal did you retain with that wire design?
So our initial contract was to retain 80% of the signal. And we did that. And then the customer came back and said, okay, now we want 100% of the signal back. So we said, yeah, give us $3 million more and another year, and we'll come back with 100% performance. And so we came back and refined it more and got 100% of the performance back. But it took a little bit more time.
So in one of the slides, you are showing about the heated air design, and you are showing that inlet, outlet, manifold, attachment ring, and the RF transparent shells, you know? So if
yes, RF transparent shells, yes.
What exactly those are for? Like,
so the material is transparent to RF.
How much frequency? Like, what are the RF frequency means megahertz or gigahertz range?
It depends on the radar. We design and develop hundreds of different types of radar. So the answer is yes.
So all sorts of frequency they can.
Yes.
Okay.
And so we have a team called the non-metallics team that develops material specifically for each different radar frequencies.
Okay, great. Thank you.
We have a follow-up question from our YouTube viewer. How did you do it to gain the 100%?
So I'm a thermal guy, right? So my job was to try to get the wires as close to each other as possible, because the closer they are to each other, the more temperature uniformity that you have. But then you have experts on the RF side that were saying, yeah, but the closer the wires are to each other, the more you hurt the signal. And so we actually, based on the wavelength of the radar, we specifically designed the spacing and the shape that you see there to minimize the interference. So it's basically working with the wavelength of the signal and using a model to predict the interference. And so we basically played with the shape and the spacing to minimize the interference. I was just rooting for the wires to be close to each other, so to improve the heat transfer. Go ahead.
Oh, apologies. I think they accidentally unmuted. Go ahead.
Yeah. So it was, we had a whole team on the RF side that was modeling the RF performance, and we would look at different designs and try to predict the performance based on the different designs. And we finally fine-tuned it enough to get 100% of the signal integrity. I was just, as a thermal person, I was making sure we had enough heat flux to heat up the surface to the temperature that we wanted in the harsh conditions.
Yeah, sounds good. Thank you. So there is one other question, like what was the most challenging part of your career or education? And definitely, what was the most rewarding?
Can you say that again?
So what was the most challenging part of your career or the education? I believe one of the students was asking, and
Okay.
and also what was the most rewarding one, you know? Both the challenging and rewarding, like that's about your life, you know? Yes.
So I will tell you that, let me go to, can you see me now?
Yes.
Let me close the window, sorry. Oh. So I would say that, you know, undergraduate school is pretty difficult. It was difficult for me, undergraduate. As I got into graduate school, I found it easier. Because in graduate school, you kind of study the things you're interested in. And in undergraduate school, you study, you know, economics and history and writing and things you're not so much interested in. So I think undergraduate was pretty challenging for me. The other challenging part was the qualifying exam for the PhD. that was pretty difficult. I failed it the first time, actually. It was pretty tough. That was probably the biggest challenge, was the qualifying exam for the doctoral degree. And the most satisfying part was finishing finishing and defending the dissertation. It was a big weight off my back.
I believe it's true for most of the people who have that, went through that process, you know,
Right.
qualifying exam, thesis, yes. So one last question about your design, you know, did you know that going into that project, like 0% loss, is it possible?
No, we don't know. Much of what we do at Raytheon, you know, we're doing it for the first time. And, you know, nobody has done it ever before. So you don't know if you're going to be able to do it or not. And the other thing is, you know, when I first started doing this anti-icing, I knew nothing about anti-icing. You know, I'm from the Valley. hadn't even seen snow before, you know. So somebody had the bright idea to get the Mexican kid from the Valley to do an anti-icing problem. So one of the things you have to do as an engineer, if you really want to advance quickly, is to volunteer to solve problems you've never solved before. Don't be afraid to do that. You know, tell your boss that you've never done it before, but you'll try it. And that's what happened to me. I had never done anti-icing. I knew nothing about it. I had no idea that the density of ice was 1/10 the density of water. I had no idea. But you know, you learn all these things, and if you enjoy it, you're gonna work hard at it. You're gonna research it, and you're gonna come up with solutions. So I would say 90% of the things I do at work, you know, I have no clue if they're gonna work or not, because nobody has ever done them before. So we challenge ourselves, and most of the time we come up with a pretty innovative solution, and you know, get rewarded for it by our customers.
Okay, guys, any other question? We are almost at the end of our, I think, session. Thank you, Dr. Mauricio Salinas, again for this engaging speech and presentation. And thank you for joining us. We really are proud of you because you are our alumni, you know, and we're going to look forward in future more engaging session with you, you know. And I'm going to give the floor to the Joan. I think she most of the time asks to everybody to turn on the camera and to have a pictures, you know. Joan, let's go ahead with that.
Yes, but before that, let's go ahead and say goodbye to our YouTube viewers. Thank you for joining us today, everyone.
Yeah.
Bye-bye.
Bye.